right, here's our next example. It's the same directions. Find the orthogonal decomposition of V onto W. But now we're going to do this with chevrons, just to show that you should be able to get used to working with both formats. Our task is to find V1 and V2. And we know the procedure. So V1 is the projection of V onto W times W, which is V dot W norm of W squared times vector W. So V dot W and then W is 1, 1. So 1 times 1, 3 times 1, we have 1 squared plus 1 squared. Square root squared cancels. So this is 1 plus 3. 1 plus 3 is 4 over 1 plus 1 is 2. Square root squared is still 2. And so this is 2 times the vector 1, 1, ordinary scalar multiple. This is 2 comma 2. So this is vector V1. Vector V2 is you take the original vector V and subtract off vector V1. So V2 is the original vector V, subtract off the V1 we just found. So the original vector V is 1, 3, minus the vector V2 or V1 we just found, rather, V1 is 2, 2. And this is straightforward, subtract component by component. 1 minus 2 is negative 1, 3 minus 2 is 1. And there's vector V2, there's vector V1, there. Now, the last piece is you don't need it because I didn't use it in this computation. You don't need the picture. But I do want to sort of draw a sketch of what this represents and show that we have indeed found the rectangular box within which vector V falls, one side of which is parallel to W. So vector V is 1, 1, 2, 3. So there's vector V, is the white vector. Let's say vector W is 1, 1. So there's vector W. And then we need the projection. So V1 is going to be this blue. V1 is the projection of V onto W. It looks like we need to extend that slightly. And so this is vector V1. And within the limits of my badly drawn picture, 2 comma 2. And then the green is negative 1, 1. That's vector V2. And my picture is terrible, but that's the rectangle we found. We've decomposed vector V into V1 plus V2, where they are orthogonal to each other, and V1 is parallel to the given vector W.